So, now let us see the remedy via these so-called perfectly matched layers. Okay. So, as I mentioned, this is a relatively newer development in the field proposed by Berenger in 94, and subsequently many people have reinterpreted and reformulated the same idea. Okay. So, let us just sort of list out the two advantages that we will get from this. Okay. So, the first is going to be that it works, it absorbs waves at all angles. Okay. So, R is equal to 0 for any angle, and the second one is it works for evanescent waves. So, in some sense this is our wish list, and nature is kind enough for us that this so called PML thing, it satisfies both these items of the wish list, which is why it was a very good discovery in the field. Now, we will when we try to formulate this, let us first, before I formulate it, I want to give you a little bit of motivation. Okay. So, let us say that this is my computational domain over here, okay, and this wave is coming over here, maybe it is coming at this angle, whatever, variety of different angles, and I am talking about, let us say, this boundary. So, these two boundaries are not important. So, waves are coming at all angles over here, and we are finding that with ABCs they get reflected. Okay. Now, if I wanted to not have that reflection, one way would be to absorb whatever falls on it. If I can somehow absorb what falls on it, there will be no reflection, right. I mean, this your simple example, if you go to a room and you speak, the walls reflect, but if the walls had some absorbing material, you will not be able to hear your echo. That means there is no reflection. So, the idea is that maybe I can put some material over here that absorbs. Now, can I put an ordinary material? If I just put something with a large loss coefficient, will it work? There is a sudden change in refractive index, right. So, even for normal incidence, the reflection coefficient is n minus 1 by n plus 1. Now, if n is anything other than 1, there is a reflection, even if it is complex, right. For a lossy medium, the refractive index n becomes complex, there is going to be a reflection even though the loss is there. So, how will you get around this? It does not seem that just pure absorbing material is not going to do it. Any creative solutions from here? Very good, right. So, one is if the loss, so let us say normal incidence, simple case, reflection coefficient is n minus 1 by n plus 1, this is n, right. So, the suggestion is make the loss increase slowly, right. What is a more technical word for slowly? Adiabatic. What is slow increase? So, it is called, so the correct word is adiabatic. So, in other words, supposing this is the boundary over here, right, 0, and the loss part, what you can do is you can increase the loss part like this. Right, and the boundary is sitting here, this is your boundary. So, at the boundary, what is the value of n? 0 loss, right. So, at the boundary, the value of n is 1, right. Then I begin, so the wave in some sense enters inside, because it seems that there is nothing, it slowly enters inside, and by gradually increasing the loss factor, you are able to gently absorb it. Okay. So, this is, I mean, some people call this a poor man's or poor woman's PML. Okay. Increase the loss gradually, the reflection coefficient is greatly reduced. Okay. So, this is one reasonable way of implementing, getting around the fact that all angles have some reflection. Now, so we've arrived at the fact that I need some special kind of loss in this in order to satisfy my wish list, right. So, you can, if I tell you that the PML is a special kind of absorbing material, you can see the motivation. We have already come across, just by simple common sense, we have come up with one kind of absorber in which where the loss increases gradually, right. So, there are two interpretations of PML in the literature, okay. So, one of them is going to be what is called as extending our logic. We will call it a absorbing material, okay, but not just any absorbing material. That material will turn out to be anisotropic. So, I am just giving you information right now, I am not deriving it for you, okay. So, an anisotropic material, right now we have only been dealing with isotropic material, where whichever direction you go the loss is the same, but it turns out that if I create different losses in different directions, I end up with a material that is a very good absorber, okay. The second interpretation is a more mathematical interpretation, okay, which is called the coordinate stretching method, okay. Both of these give the same values of your epsilon and mu in for the PML, okay. So, it is the same principle seen from two different ways. The first way is a physics based way, the second way is a more math based way, okay. So, this is physics, this is math, okay. Now, which interpretation are we going to choose? Yeah, right. So, we are going to choose the math based interpretation because the math gets easier if I choose this interpretation, right. The physics based interpretation is very appealing, but the math becomes more complicated because the moment I have anisotropic medium, then I have to start dealing with tensors and all of that, right. But this coordinate stretching is a very beautiful and simple way of arriving at this thing. Okay, so what we do in this coordinate stretching approach is going to be very interesting. So, what is our usual Maxwell's equations? Again, the beauty of this method is starts with Maxwell's equations. So, let us just write down our usual Maxwell's equations, right. So, curl of E, right, and let us keep matter simple, we will assume j omega t time dependence, right. So, this becomes minus j omega mu h, curl of h I will write as j omega epsilon E, right, and similarly the other two equations, okay. Now, here itself is where the coordinate stretching approach presents a very interesting way. So, what it says is, let us reinterpret the del operator itself, okay. So, let me write down the other two equations so that you know that I am going to do it to all of these equations. Okay. Pardon me? The material, yeah. No, all of that is absorbed into epsilon. So, epsilon can be complex, okay, and mu also can be complex. So, what I do is I redefine this operator itself, okay, in a way that I will describe right now, okay. So, what is this del E? So, this del E, so let us write down del first. So, what is del? X hat, right. Each of these three Yeah. Now, what is del E? Right. So, as the word coordinate stretching suggests, each of the coordinates is going to get stretched by some number which I choose. And what is that number? It looks strange, but that is going to be the approach. So, I am redefining the operator in this. So, I have now left the physical world away. I have entered a mathematical world where I have created a new operator called del E, which agrees with the physical world for values of Ex, Ey, Ez equal to 1. Okay. This is small Ex, small Ey, small Ez. These are scalars, they have nothing to do with any physical constants. Okay. Similarly, this del H, I will just write it in slightly smaller notation, 1 by Hx, 1 by Hy, and 1 by Hz. These are the new operators. Okay. So, if I take these operators and try to solve a wave equation from here, okay, do you think the form of the solution? So, we know that for a wave equation the solution is exponential e to the plus minus jkr. Time has been dropped out of here, correct? In this equation, if I take this interpretation over here and I rederive the wave equation, what do you think will happen? Will I still get a wave-like solution? Just intuitively, I should get a wave-like solution, except what will happen? This 1 by Ex square will come somewhere, 1 by Hx square will come somewhere. So, I will get a wave-like solution, but that wave will have that factor of Ex or Hx or whatever in the exponent, right. So, you can work it out, I am just giving you, it is very simple. Once you just put this out, take a 1D wave problem, put it in, and you will find that I still get a wave-like solution, okay. So, we can say that E is equal to, so I will get some E naught e to the plus minus j k dot r is a solution. Now, if this is going to be a solution, then this k needs some interpretation. Yeah. Okay. So, we should expect that somehow these E's and H's, small E's and small H's will appear inside this K somehow, where else, right, it has to go somewhere, there is no way for any of it to cancel off. Okay. So, it has been a little vague so far, but now what we will do is to drive home the point, let us take a 1D example. Okay. So, is there a relation between Ex, Ey, Ez? You should ask more. Is there a relation between Ex, Ey, Ez, Hx, Hy, Hz? Answer is yes, we are getting to it. Okay. How will those relations come? I mean, when we start putting in Maxwell's equations, wave equation, those relations will come. Okay. So, you should remember one thing, this is not what nature has given us. We are doing these manipulations to get these desired objectives out of it. That is, so remember, it is an engineering tool kind of a thing that we are doing. We are scaling the coordinates within the operator, okay.